Let's talk about Earth's climate. We've already talked about atmosphere before, but I want to actually break this down for you because when we look at atmosphere, it's not all the same. So in our atmosphere, we look at about 99% of the atmosphere being made up of nitrogen and oxygen, fine. Low levels of CO2 typically. And we see some argon and some methane and things like that. But what we're most interested in this troposphere, or this lowest level, this is where we live. Okay, so if this is your house, it's from this ground level up to 7.4 miles. This seems arbitrary to you, I understand, but that measurement is actually due to the pressures and the temperatures associated with that section of the atmosphere. And I bet you never really thought about the fact that you're walking around an atmosphere. That's okay. Above our troposphere, we actually look at the stratosphere. So tropo's at the bottom, stratosphere's next. And stratosphere, we've talked before, contains huge amounts of ozone. Remember, ozone is made through a combination of UV and oxygen, giving us O3, right? Well, the whole reason we want ozone is to block UV. By blocking this, it blocks about 99% of the UV coming out of the sun. It allows us to live on this planet. If that ozone was not in place, this would still be a very harsh environment and we wouldn't be able to live here. What we are interested in is this buildup of greenhouse gases, and we've always had greenhouse gases. This is nothing new. The only reason our planet is warm is because we have this layer in the stratosphere of greenhouse gases. CO2, methanes, things like that. Our planet has always produced those, okay? But what we want to look at when we talk about climate change and global warming is an increase in those greenhouse gases, which increases the temperature on the planet. But we need it there. Without it, it would be like everyone lived in the desert. It would be scorching hot during the day and freezing cold at night, regardless of where you lived. So it acts as a terrific blanket or insulator around our planet. Our concern, as I mentioned, is that we're increasing in temperature from average much more rapidly than we would predict. Okay, so when we look at the beginning of the Industrial Revolution, roughly, since that time we've seen kind of this continual increase in temperature. Now, you should note that throughout very long periods of time, we do see fluctuations in the temperature on this planet. We get it from things like tree rings. Ice cores in particular have been the most important for helping us to track these temperature changes. But I don't want to dwell on this today. What I want to think about instead is what it actually means to have a climate. So when we talk about climate, we can talk about sunlight, we can talk about temperature, all of these things, but what we need to focus on in particular is the amount and the intensity. These are different things. The amount and intensity of light or sunshine that's hitting our surface of our planet, because this is what actually influences temperature. And temperature with water drives climate. Okay? So what we want to look at is the fact that our planet is actually tilted, right? It doesn't sit straight up and down. It's tilted at about a 23.5 degree angle, okay? And as it tilts and rotates around the sun, when you're closer to the sun, so at the equator here where we get sunlight hitting pretty directly, things are warm most of the time, right? Okay? But when we look at this low angle of sun coming in and hitting our North Pole here, do you think it would be winter or summer in the North Pole right now in my picture? What about in the southern hemisphere, down here in Antarctica? They don't even put it on the map, right? Down here in Antarctica, do you think it's winter or summer in this diagram? Well, let's think about it. When the Earth is tilted, right, and points, this is the one that's equivalent to our previous picture. So tilted so that the southern hemisphere is closer to the sun, it's actually December. Well, is December winter or summer for us? Of course, it's winter. But when we look at the shift then, if we keep going around the sun, eventually the northern hemisphere is tilted towards the sun. Okay? As it tilts towards the sun, that's what we call our June solstice, or the first day of summer in the northern hemisphere. Now, yes, while our planet is orbiting around the sun, it's also spinning on its axis, right? So we have to deal with that. But what we're most interested in with climate is this tilting, or this positioning of the sun, or positioning of our planet relative to the sun. Now, the spinning adds a different dimension to all of this, and it actually looks at generating what we call Hadley circulation cells. Essentially, the spinning is setting up wind patterns. And when it sets up wind patterns with this rotation and the tilt of our planet, we set up these scenarios where we get high temperatures. So if you have high temperatures, you have a lot of evaporation, right? And particularly around the equator, look at all this water, right? So if we have high temps, we have high evaporation. When we have high evaporation, the wet air rises, condenses into clouds, and actually starts to fall as rain back to the surface. So you know that the equator is not only hot, it's also wet. Rainforests, things like that, right? Okay. But as that air moves, so as our planet spins, this air is actually going to move around. And as it does, when it gets up to about 30 degrees north and south, you see this is mimicked both sides, or a mirror image of itself. When we look at this air coming back down again, it's very, very dry air because all of the water in those clouds was already dumped out. So the air is very dry. Well, if you have very dry air, what are you going to get as a climate? Deserts. North and south, 30 degrees, we get desert. And then it continues. Air circulates again. We get the same pattern of air rising, water falling. When it does, we get that water falling at 60 degrees, north and south, and high rainfall. But then again, air circulates. We've got dry air that falls at the poles. The poles are equivalent to cold deserts. Okay? So when we look at this process of circulating air and moving things around, why are we so interested in this? Well, I'm very interested in this because these kinds of patterns are actually going to help us set up the mechanisms by which ecosystems or biomes are formed. So you see I have here tropics and temperate. So in the Northeast, we're kind of in this temperate zone. Some of you may have visited the tropics at the equator, right? 0 degrees is the equator, all right? So this constant circulating of air and the spin of the planet and the cycling or the orbit of the planet around the sun sets up this complex mechanism in our ecosystems on this planet. Now, my pink arrows here actually are going to indicate the direction of the wind on our planet. And in the northern hemisphere, we have a lot of what we call westerly winds. So the storms often come in from the west, right? And if you've ever flown from the east coast to the west coast and the west coast back again, you know that the flight time is longer from east coast to west coast than west coast to east coast. Why? If your plane is flying this way, it's flying into the wind when it's going east to west, and it has what we call a tailwind coming west to east. So the winds literally push your plane across the U.S. Kind of cool. But depending on where you're going, those tailwinds and headwinds would be very different. Right? But all this mess together forms essentially these bands of climate across our planet. So we already talked about the fact that the equator is hot and wet. You see here over 150 centimeters of annual rainfall. Very, very wet. We get all kinds of rainforest type situations in these areas. Now we do have some dry spots under 25 centimeters annual rainfall. We mentioned the poles being very, very dry at 90 degrees north and south. Of course, they don't have Antarctica on here for you, but 90 degrees south would be a cold desert as well, right? But then when we look at some of these other patterns, things aren't as clear. Like, what's going on down here? Why is half of the bottom of South America wet and half of it's dry? This is bizarre, right? So what we have to think about is other factors associated with climate, including things like Gulf Stream and ocean currents, because the ocean currents actually provide warm or cool water to areas, and that significantly impacts their climate, particularly in coastal zones. Why? Well, what we look at are these physical barriers to our circulation patterns. So everything is laid out as we've talked about. The problem is when we add things like mountains, right? So when we add mountains, if you've got a mountain range and the winds are coming in here from the left-hand side of your screen, the winds are bringing in moisture typically. And when the moisture comes in and the winds come in, it's trying to get up and over this mountain if you have these clouds, but the clouds can't push up and over the mountain until they drop their rain. So it's rainy on this side of the mountain, but when the clouds lighten up, they've dropped all their rain and they go up and over the mountain, the fluffy clouds on this side, no rain. The water's all been dumped out. So this side of the mountain range is very, very dry. We see this. Not only do they change precipitation patterns, they also change temperature patterns. So with, of course, changes in altitude in our mountain, the further you go up the mountain, the colder it is. Okay. And we can see huge effects of mountain ranges in temperature and rainfall patterns compared to what we would expect in these areas. So here's a better graph than my mountains I was drawing to show you. Rain coming in off the Pacific, so this is in California. Rain coming in off the Pacific, pushing up and over the coastal range and then up over the Sierra Nevadas. And when it does, the rain has to fall so that the clouds can get up and over the mountain. And when the clouds get on the other side, if there's even any clouds left, right, because clouds are all moisture, they're all water vapor. So once they dump out all their rain, we end up with what we call a rain shadow or desert on the other side of the mountain range. So all around our planet, we set up, with all of these things taken into consideration, these very distinct biomes. There's that word again. Thinking about biomes or different types of ecosystems. This is outlining just the terrestrial biomes for you. You can also talk about aquatic biomes, so you look at the difference between freshwater and saltwater. But just to give you a sense of how things kind of break out. And in a lot of cases, we have this east-west pattern that we would expect. But then weird things happen and we get north-south patterns, right? And poor Australia, it's got all kinds of weird things going on. So just keep in mind, when we look at climate on this planet, it drives everything about ecosystems as far as their abiotic components: light, temperature, water availability, all of these things.